I'm Jim Brickmeier. I'm Senior Vice President of Strategic Marketing for Concurrent. Some of you may have heard of Concurrent in the past. I'll give you just a very quick update on the company, who we are. We're a supplier of solutions, software and solutions for mission-critical applications. So when you take a look at the solutions that we provide, everything that we provide is based on a core of high-performance Linux and storage. We provide solutions, content delivery solutions, into a variety of customers that you may know, so folks like Time Warner Cable, Charter Communications, Rogers Communications, and others. We also have real-time applications where we supply technology to 19 of the top 20 automotive manufacturers for simulation and testing. We also supply our Linux operating systems to the U.S. Navy, to a variety of high-performance companies, to NASA, as an example, for things like the Orion space program, use our Linux operating system for things like that. So what I'm going to talk about today is about optimizing content delivery really on open source platforms. So when we take a look at what's being used today out in a lot of CDNs, and a lot of service providers are also looking at open source technologies for their mission critical CDN applications. So there are a variety of technologies that we're going to talk about today from a server standpoint. Things like the Apache traffic server. Comcast, as an example, has been using ATS and has come into this forum to talk about how they're using it. We have many customers who are looking at things like that, and so we've done a lot of investigation into that, as well as things like Nginx. Transcoding, so things like FFmpeg and Handbrake. Also looking at storage solutions, so like Ceph as being sort of an up-and-coming open source storage solution. Things like OpenStack Swift, and then of course the underlying operating system being Linux. And we'll talk about how we can optimize these types of technologies. Okay, so when we take a look at open source technology, first of all, for mission critical applications, and mission critical in this is effectively anything that's vital to the functioning of an organization. So when we think of a CDN, if you're a video company, the CDN itself is absolutely critical. You don't generate any revenue if that system goes down. So when you look at mission critical applications, taking open source technology and trying to apply it into that environment is sort of like trying to build a race car out of general purpose components. So the challenge here is that while you may be able to take all those piece parts, which are sort of designed for general purpose use, and piece them together, you probably wouldn't want to do that and take that out on a racetrack. So you also wouldn't want to do that and take it out into a mission critical kind of an application, because what you find is that while open source tends to be very flexible, and it's open, and it addresses the cost considerations, it doesn't really address all of the concerns on the right-hand side, which are performance, reliability, and efficiency related, things that are specific to the types of applications that you're running. So that's what I'm going to talk about today, is basically how do we optimize open source technology so that we can apply it into these mission critical applications and get some better performance out of it. Okay, so I'm going to start out with Apache Traffic Server because, from our standpoint, we see a lot of customers interested in using this as part of their CDN framework. So it fits this profile of open source very closely. When we look at the capabilities of Apache Traffic Server, first of all, it is flexible in the sense that it gives you, HTTP web caching capability. It is open, so there are APIs, and you can put plugins associated with it in order to try to tailor it, and it's very, very low cost. But when we start to look at the performance of ATS in the network, what we find is that the output performance of ATS isn't really as optimal as it could be when you compare it to alternative sort of proprietary or purpose-built types of caching solutions. From a reliability standpoint as well, there are things left to be desired in terms of its resiliency in some of the video scenarios. And then from an efficiency standpoint, a lot of the algorithms that ATS uses as part of the standard offering aren't really optimized for video streaming applications. And we'll talk about ways that we can enhance ATS effectively to make it more applicable and more efficient in video architectures. Okay, so first of all, I wanted to highlight some of the optimization opportunities here. So first of all, output performance is one of those items which, in order to gain efficiency on x86 hardware, the idea is, let's pump as many bits as we can out of those servers so you can reduce the number of servers you use environmentally, try to keep the power costs and air conditioning costs down. One of the things you can do there is use a high-performance Linux operating system in order to improve that output performance. And we'll talk about a little bit later how you do that, how you can actually tune applications like ATS to leverage more of the hardware capabilities. From a cache efficiency standpoint, there are better caching algorithms than what is natively included with ATS. From a resiliency standpoint, you can do things like cache failovers, so that if you lose a server, if a server were to fail, when you lose that local cache, you don't actually lose all the content and create a situation where you're pulling a bunch of traffic across the network. And then in terms of app-specific features, there are things that when you take a look at ATS specifically for a video network, you can introduce things like just-in-time packaging, just-in-time transcoding. You can introduce things like the ability to stream RTSP traffic from an Apache traffic server. All of these are app-specific types of functionality that you can layer on top of Apache traffic server. I'm going to talk about a couple of these examples today because I only have a short time. So let's start out with the caching, cache efficiency discussion. So first of all, the ATS server, as I mentioned, is sort of a general purpose cache. It was designed for web content, okay? And it was designed in a day where there wasn't quite as much video streaming traffic as there is today. So what we're seeing is during peak periods, in some cases you have 60, 70, maybe even more of the content traversing a lot of these CDNs as video traffic. And so really the focus is heavily on video in a lot of these caching architectures. What we find is that ATS natively does not really handle byte range requests very well, which when you're watching video, there are a lot of people that enter videos in the middle, so they'll pause live TV or they'll switch channels and they'll come back. And what happens is the client will actually request particular byte ranges from the CDN. What actually happens with ATS, where I'm giving you an example here for Consumer One, is that Consumer One has requested through their client a request byte ranges 100 through 200. The ATS server, if it doesn't have that in cache, will go out and pull that content from a CDN, fill it into the cache, and store it. What we see is that when Consumer 2 comes in, if their client asks for byte ranges 150 to 250, even though you're actually caching from 150 to 200, the Apache traffic server doesn't understand that there's an overlapping set of content there. So the ATS will actually cache that content again, and you get duplication of content in the cache. What you see is that continues again here where you have a byte range of 100 to 150. Again, we've duplicated content in the cache. So as that happens repeatedly, you're just consuming space unnecessarily on the edge server, and you're also pulling a lot more traffic over the network than you need to. And so the idea here is that you can optimize the cache for video to understand that effectively what is an asset. So the cache manager itself can actually make those determinations, can interpret byte range requests more effectively. And in this scenario, what you see is that the first consumer makes that request for 100 to 200 in terms of the byte range. When the second consumer comes in, there's a recognition that most of that content is already there. So you don't have to pull the content again. And by the time you get to the third consumer, you're not pulling any traffic. You're just effectively using what's already in the cache. So very efficient from that standpoint. And again, just an algorithm that you can plug in to ATS to make it work much, much better. What we also see in terms of the caching capabilities of the ATS server is that typically ATS is used this way with a Straight popularity ranking is how you actually expire things from the cache. So as you start to fill up the capacity of the cache, it will do this least recently used algorithm and say whatever is least recently used, we're going to go ahead and drop that from the cache. Now that's sort of a very simple kind of a mechanism, and if you don't know what kind of applications you're running, and this, again, if it's general web traffic, that makes sense to go ahead and do that. But if you're looking at a video CDN, there are a lot of other considerations. So you can implement an enhanced caching model that gives you much more attributes that you can go ahead and use to prioritize content. Some of the things that we look at are things like source. So where is the content coming from? You may have multiple different types of sources. You may have public clouds. You may have private clouds. You may have private networks, things that don't cost you any money to go ahead and transport content. In other cases, it may have to go through an internet peering point. Service types, so revenue-producing services versus free services, and content type as well. And so the idea here is that by implementing a more sophisticated caching model, you can take into account the reliability of the sources where you're gaining content from. So as an example, if you know that you're going to pull content or you're pulling content from an unreliable source, you don't want to expire it from the cache because the likelihood is, 50% of the time it may be that I can't get access to that content. I want to keep it in the cache if I have it. So you may also, as an example, for service providers that are pulling content through a peering point and they pay money for that, they may say, if I have to pull it through a peering point, I don't want to expire it from the cache. I've already pulled it once. I've paid effectively for that bandwidth, and I'm just going to keep it in the cache as long as I possibly can. And if it's part of their private network, which there's no cost in their mind attributed to that, they'll go ahead and expire that from the cache and pull it again. You can also prioritize high-value content services and say, pay content, I'm going to keep it there because quality of service would be better as opposed to free content, which I'm less concerned about. Some other things you can do from an ATS standpoint, what I'm showing here is building in things like just-in-time repackaging, dynamic DRM application, and things like policy controls and manifest manipulation features. So you can add in SDKs into the Apache Traffic Server framework so that you can do things like just-in-time repackaging or even just-in-time transcoding. So the idea here, as you heard in the prior presentation here, is take one source format, keep that consistent throughout the CDN, and then adapt the content at the edge so that it can fulfill effectively streaming for any device. Okay, now I'm going to talk a little bit about optimizing at the operating system level. So this is something that we've been very focused on as we've taken a look at some of the open source software and things that are specifically CPU intensive. So there are opportunities within the operating system to go ahead and tune applications so that they perform better. And we've got an example of one which I'm going to show you in just a second. But the idea here is that you can use the OS to actually prioritize threads, to shield CPUs, to allocate and basically revector interrupts so that systems perform better and more reliably. What we've seen in a lot of the open source software is that it works fine under perfect conditions, but as you start to hit it with other types of activities, or if you've got a hyper-converged framework where you've got multiple applications running, all of a sudden performance starts to drop off and nobody knows what's happening, right? So this is where the operating system, using something like a real-time operating system with real-time schedulers, becomes very powerful. So one of the applications that we have been working on here is taking a look at live and file-based, effectively just-in-time transcoding workflows. So we took an example here. We used a commercial software-based transcode solution, but it could just as well have been FFmpeg in order to do this. So what we do is we take that application and we run it with a high-performance OS and a set of optimization tools so we can see under the covers and effectively see what's happening to the application. What we're showing here on the screen is effectively what you see. These are different CPUs, and you can see those little lines that go up and down are interrupts that are happening against the CPUs. So typically, that suggests that housekeeping functions, various kinds of inefficiencies in the code are coming in, and while I'm trying to do a transcode, something's coming in and hitting the CPU and saying, hey, you got to do something else, and then you got to come back and continue your transcode. So when you see this kind of wavering line, it suggests that this is not a particularly efficient type of transcode. And by the way, this is a commercial product, so this is something that's shipping today to customers and is considered an efficient transcoding product based on the people who sell it. So we were able to come in there and take a look at that and say, effectively, it's not as optimized as you think it might be. Aligning the I/O threads to CPUs, you can do thread prioritization and shielding, as I said. And basically, one of the comments that we got from the manufacturer of this transcode solution was, we didn't think that when we moved to a pure software-only infrastructure, coming from really doing everything in hardware environments are very deterministic. So you know what you're going to get. Software environments are less so. And what their response was after they ran this was effectively through software, I'm getting hardware level determinism. And so I can get roughly equivalent types of performance exclusively through software. So what you see here on the right-hand side, again, just looking at the number of interrupts that are happening, you sort of clear those out and protect those CPUs so they actually stay focused on the real-time transcoding functions. What we see is that for things that are more CPU intensive, you can improve things like transcode density. We have actually seen improved output jitter and faster transcodes. So overall better performance we've seen just in very, very quick circumstances where we took the OS and the tools. Within a day, we can get 20 to 30% improvement if you spend more time with it, or if you look at things, there are also opportunities for GPU acceleration of transcode applications like that. You can get even more. So a very powerful solution, and again, it works for anything that's CPU intensive. Transcode is just one example. And the nice piece about this is in cases where, as an example, we take Apache Traffic Server if we want to do transcode as an embedded part of ATS. This allows you to protect the ATS functions and then also protect the transcode functions so they don't overlap each other. They all perform exactly the way they're supposed to every single time. Okay, so another example here is taking software-defined storage frameworks. We're using the example of Ceph here. And again, Ceph sort of falls into that same profile. Again, it's a very flexible object storage platform, supports block and file storage as well. Flexible interfaces, very low cost. You can run it on commodity hardware. And again, what we see is that from a performance standpoint, scale's really, really large. You can do exabyte capacities. The challenge has to do with the performance, the throughput, the reliability of that system as you start to load it up. We also see things like erasure coding, which makes object storage more efficient, start to dig into the capabilities of those systems. So the idea here is that what you can do is wrap these optimization layers around the Ceph software, and in doing so, you can get a much better product that's more applicable to things like mission-critical applications. So these are just some of the example types of optimizations that you can do against software-defined storage architectures, Ceph, OpenStack, effectively any of them. So at an OS level, again, you can do the same types of things that we showed for transcode, anything that's CPU intensive. If you've got storage architectures where you're doing encryption, or you're doing transcode, or you're doing erasure coding, anything that's CPU intensive, you can go ahead and effectively protect the performance of the system and make sure it works the way that you want it to, very reliably. You can also layer a variety of other things on top of this in terms of how you access data within an object store. You can do distributed software clients so that rather than having to go through gateways, you can access each storage node independently, which increases the utility of the solution overall. And of course, instrumentation is one layer on top of that, which allows you to manage all this. And as you take a look at performance over time, because you have access to these types of tuning and optimization capabilities, you can see what's happening under the covers, and you know when you actually need more capacity, which is one of the most important things as you start to scale out these systems. So, so basically the message here is, look, with open source software, if you're going to build a race car, if you're going to build a mission critical application, taking general purpose parts and trying to piece them together is not as easy as it sounds. It's something that you do have opportunities to go in there and basically make it gel together, so you actually build a high performance machine out of all that object storage and get a better performing solution. So I'll take questions.
Do you see a difference between the performance of the Apache traffic server and Nginx, or your point is that it doesn't matter, that they both can be?
They're both pretty similar, actually, and so and they're aficionados of either, right? So we've heard folks who love Nginx versus ATS, and there are pros and cons. So some are more flexible or have more features in certain areas. The idea here is that both of them are designed for general purpose, right? They weren't designed for your specific application. They weren't designed for specific hardware scenarios. So you might be running in a blade architecture. You might be running in 2-rack unit. And what we've seen is that all hardware is not designed equal. So you can actually go in, and depending on what your framework is, you can find a lot of different optimizations that you can take advantage of. And that's effectively, we've done this for many years as we've worked on things like stuff in the space program and the US Navy and other types of applications. What we've done now is taken that core expertise and an open source Linux operating system and these optimization tools and really applied it towards open source so that you can get the advantages of that type of system. Yeah, so for Apache, we're actually still running through all of the details for the Apache in different hardware scenarios to see the output performance enhancements and so on. So we haven't published all that information yet, but we will. So we're going to put out a paper, and if you give me your card, I'll get you a copy of it.